Night after night, the sky over the fleet looked the same. Black water, black steel, and the thin, pale streaks of incoming aircraft that seemed to arrive from nowhere. Anti-aircraft crews could do everything right: range, lead, fuse setting, and still watch shells burst too early, too late, or not at all. A battleship could throw a storm of metal into the air and still feel helpless. In the mathematics of anti-aircraft fire, the cruel truth was simple. A direct hit on a fast, small, moving aircraft was rare, and near misses meant nothing if the shell waited to touch something before it exploded. So the war kept asking the same question over and over in smoke and salt wind. If the gun cannot guarantee a hit, can the explosion be moved to where a hit is no longer necessary? That question produced one of the most guarded objects of the Second World War. Small enough to fit into the nose of a shell, fragile enough to look impossible, and yet tough enough to survive the violence of firing. It was called the proximity fuse, also known by its wartime label, VT, variable time, a name chosen specifically so it would not explain itself. The principle was cold and elegant. Instead of guessing the perfect time to detonate, the shell would sense a target nearby and explode in the air at the moment the target entered an optimal burst zone, a ring of space where fragments, blast pressure, and shock could actually kill. It was not magic. It was the conversion of anti-aircraft fire from hope into probability. And the most important part was not only the device, it was the system built around it. Radar tracking, fire control computation, standardized drill, and relentless quality testing that made millions of fuses behave the same way. Every time. The proximity fuse's promise was often described in brutal multipliers. In general terms, a proximity fuse could increase lethality by several times compared with contact or time fuses, because a shell no longer needed to collide with an aircraft to matter. But the deeper point was less glamorous and more decisive. The fuse moved the explosion to the place where physics did the most work. In that narrow window of distance, too far and fragments thin out, too close and geometry can betray the burst, there is a best place to detonate. VT fuses were built to chase that place. Automatically, their job was to create an airburst at the moment a target was close enough for the shell's fragments to bite. This was not a single inventor's miracle. It was a wartime industrial choreography. The U.S. Navy initiated the effort early in the war years, pushing a problem that many believed could not be solved. Miniaturize electronics. Make it survive extreme acceleration. Make it arm safely after firing. Make it function reliably in cold, heat, humidity, and vibration, then manufacture it by the millions without losing consistency. That last requirement mattered as much as the first. A brilliant fuse that only worked sometimes was not a revolution. It was a rumor. So the process became as important as the product. By war's end, roughly 22 million VT fuses had been produced, with about 1.8 million reserved for testing. The cost story alone explains how the weapon became a system. Early units were extraordinarily expensive. And then, through mass production, standardization, and constant refinement, the cost per fuse fell from about $732 in 1942 to about $18 in 1945. That price collapse was not a footnote. It meant commanders could stop treating proximity fuses like jewels and start treating them like ammunition, something that could be issued broadly, trained with, trusted, and integrated into doctrine. The war was full of inventions. Fewer inventions became habits. VT did, but technology alone did not save anyone. What changed? Outcomes was the marriage of sensors to gunfire, radar to tracking, tracking to prediction, prediction to fuse-armed airburst. One of the most cited combinations was the 90mm gun firing a VT fused shell under the direction of the SCR-584 tracking radar and the M9 gun director, turning anti-aircraft fire into something close to a controlled experiment. Detect, lock, compute, fire, and let the fuse handle the last few yards of uncertainty. In that architecture, VT was the final link, the point where numbers became detonation. That system logic is what made the kill rate story so revealing. During the campaign against German V-1 flying bombs, the share destroyed in the coastal gun belt rose dramatically over time. One widely reported set of figures describes it rising from around 17% up to 74%, even reaching 82% on a peak day. The numbers were never just VT did it. The numbers were the output of a loop. Radar made tracking real, fire control made timing plausible, VT made near misses lethal, and training made the whole chain repeatable. Remove one link, and the curve collapses. The same logic appeared at sea, where the fuse's value could be measured in seconds. Against dive bombers, torpedo planes, and later kamikaze attacks, the difference between exploding near a target and exploding after it passed was the difference between a damaged ship and a burning one. The exact multiplier could vary by conditions, tactics, and weapon, but the pattern held. When shells detonated in the optimal burst zone instead of empty air, hit probability stopped being the bottleneck. Secrecy shaped everything. Early in the European War, leadership feared that a dud shell might be recovered, copied, and used against Allied aircraft. So VT was initially restricted to situations where capture was unlikely, over water, or in theaters where retrieval was improbable. That caution is easy to forget, but it reveals the strategic stakes. The Allies did not treat the fuse as better ammunition. They treated it as a decisive method, something that could change the balance if it spread. Even the ground war eventually bent around it. Once the risk of capture was judged acceptable, VT fuses began to appear in artillery shells for airburst effects over troops and formations, famously in the late war period in Europe. One widely cited example is the release of proximity-fused shells, codenamed POSIT, used in large numbers during the Battle of the Bulge, where airbursts made heavy artillery far more destructive because shells no longer had to hit the ground to do maximum damage. The human consequence was immediate. Troops who might have survived a burst buried in mud could be cut down by fragments exploding above them, where cover mattered less. And yet, it is still tempting to tell the VT story as a clean technology triumph. Brilliant scientists, a secret device, dramatic improvement, victory. That story is comfortable because it keeps causality simple. The uncomfortable story is more realistic and more useful. VT worked because the Allies built a full pipeline of reliability. Not just invention, but testing culture, production discipline, and training doctrine that forced the fuse to behave like a predictable part. By the end of the war, more than 100 companies across the United States were involved in producing many types of VT fuses, and the system included daily quality verification, practices that treated reliability like a weapon in its own right. War is full of clever ideas. Only some become dependable. The proximity fuse also exposes a deeper advantage: abundance directed by method. Miniature vacuum tubes, metalwork, batteries, packaging, wax sealing, shock hardening, inspection, shipping, and documentation. This was industrial literacy applied to combat. The device may have been small, but the machinery behind it was national in scale. And that is why kill rate is the right lens. VT did not make gunners braver. It made their firing solutions matter. More often, it turned a near miss into a kill zone, and then made that kill zone repeatable through radar synchronization and crew drills. Faith cannot armor steel, but process can. There is also an irony. The proximity fuse is often remembered as a smart shell, but its intelligence was limited and specific. It did not see the battlefield. It only answered one question: is something close enough for fragments to matter? That narrow intelligence was exactly what anti-aircraft fire needed. The war did not require a shell that thought. It required a shell that detonated in the right place, consistently, while radar and fire control handled the larger geometry. In other words, the optimal burst zone was not a poetic phrase. It was the operational thesis. By 1945, the story had written its own proof. A device once considered too delicate to survive firing was manufactured in the tens of millions. A cost that began absurdly high collapsed into a price that allowed broad issue. A defensive problem that once required enormous expenditure of shells per aircraft was pushed down into something closer to manageable arithmetic, because the explosion was finally placed where physics could finish the work. The proximity fuse did not win the war by itself, but it revealed how modern war is often decided. Not by a single invention, and not by a single heroic moment, but by a chain that connects sensors, computation, training, manufacturing, and doctrine into one repeating act. The men on the guns still aimed. The radar crews still tracked. The directors still computed. The factories still shipped. The inspectors still rejected bad lots. The fuse simply ensured that when the system did its job, the shell's explosion happened where it mattered most. In that sense, VT was not only a weapon. It was a philosophy made metal. It declared that the battle could be shifted from the romance of direct hits to the realism of probability. It proved that close could be enough if the detonation was optimized, and it demonstrated, in black smoke against a pale sky, that synchronization beats improvisation when the margins are measured in yards and seconds. In the end, the proximity fuse's legacy is a quiet lesson in cold light. The war's most decisive advantages often looked boring on paper: tighter tolerances, cleaner supply chains, more consistent training, better radar procedure, better failure analysis, better production scaling. Abundance, not ideology, won the war. And when abundance was joined to measurement, when shells began to burst in the optimal zone again and again, the kill rate stopped being a mystery and became an outcome. If the record matters, the comments can hold the argument whether the proximity fuse should be remembered as a technology breakthrough or as proof that systems, radar plus training plus production, are the true weapons of industrial war.